SDK platform, basically, and it's a computer vision-based form of augmented reality. I work with the developer support team. My background's in engineering, and I've done some of the early work with Vuforia app development. I guess just before getting started, I'd like to get a sort of a lay of the room. What is, how many people here are programmers? Okay. Otherwise, working in 3D design, designers, development. What do you guys do otherwise? Engineering? What's your background?
Architecture.
Okay. Architects primarily?
Construction.
Okay.
UI, UX.
Okay. Yeah, so, I mean, I think what I'll do, I know this being it's a hackathon, you're probably looking for some ideas as to the feasibility of implementation of some of the capabilities that we have. So I'll get you into some of the concepts around AR and the nature of the platform and really then how that's applied as a workflow within your fields. So just to back up, you probably heard about augmented reality. It's basically the principle that you have the ability to lay virtual media into a real-world context in recognizing images, surfaces, contours that exist in the real world. There's different approaches. A lot of the early stuff was really GPS-based. It's that sort of floaty layer style of AR. There's obviously precision problems with that. The advantage of working with optical or computer vision-based AR is the precision is much better, right? So that's really the focus of our SDK. And we started working initially in the early generations from flat targets into 3D surfaces and now contours. And we've introduced depth mapping using a type of IR-based depth mapping. So let me just sort of get you into the basics of this. What I'm going to do is really review what Vuforia is, why you would want to look at Vuforia as an augmentation technology for AR, give you a platform overview, and then give you a show of some of the emerging technology in this area. And I think one of the things just of interest, to this audience is when we talk about AR, it's typically what we're looking at is that people are laying media onto objects. I'm laying an image onto this type of a surface. But the thing to remember as well is that the fact that I can infer the orientation and position of this means that I can also infer the orientation and position of the user. So it's interesting for applications in context where you want to know where somebody is and what they're looking at in a real-world situation. So it isn't simply about augmenting media onto images and that sort of thing. And again, the principle is really that what we're doing is enabling really the aptitudes of visual perception for mobile applications. It obviously isn't as sophisticated as human visual perception, but it integrates a lot of the same capabilities. Here's some of the applications that have been coming out of the past couple of years. We've been around for about 2.5 years, almost 3 years. That's a type of target that's generated dynamically. You don't have to predefine it. You can capture an arbitrary image for the purpose of augmenting it. That's an encoded marker, so it has an ID that can be extracted from the marker, and you can also use it for tracking. That's really the integration of AR into an existing device or product. Legos is big on AR. This is actually a type of application that you're capable of versioning the content and the targets and the media on the back end. You don't have to embed it onto the device. Okay. And this demonstrates video and texture rendering, which is kind of a nice feature. What this means is that when you can shoot a video and actually lay it onto the surface so that as the surface is manipulated in the camera perspective, it changes correctly from the perspective. That is an interesting app because what that actually does is extract the color of the surface and then maps it onto the model so that the model reflects the coloration. It's almost like a chameleon. That was text recognition. This is the ability to recognize cones and cylindrical shapes. It's been popular with toys. With all this stuff, I know.
I am.
Well, it's moving very quickly. I mean, it's like I said, we've been around for a few years. Our focus has really been on vision-based stuff. But what we've seen, the big uptake has been in areas like publishing, retail entertainment, as they'll call it, like product displays in shops and such, toys, things like that. So at this point, we've got about 70,000 developers. It's very well distributed, primarily North America, Western Europe, a lot in Asia that we're seeing, and a decent representation in Latin America. And these numbers are actually old. We're over 6,000 at this point. And it's primarily, we have developer adoption type commercialization apps using Vuforia SDK built for about 2.5 years, over 5,000 apps, as I said, 6,000. About 60% of those apps are on Android, but consumer usage is higher, actually, as far as the current usage on iOS. And more than 50 have over 100,000 downloads, and over 9 of them have over 1 million downloads. A lot of the big ones have been tied to like large movie marketing campaign. Red Bull is a big one, stuff like that. The Spider-Man app is one of our big ones. The Maxim app is very popular. The Maxim app, you can get it through the app markets. And one of the smart things they've done is actually they release an app concurrently. They work with Maxim concurrently with each issue, and they update all the content. So it tends to drive a lot of consumer update. And just as some examples, again, Lego has adapted it for their product catalogs. What they're actually doing is showing the Lego models in the context of the catalog. So what this is showing, that's a scan interface. They basically capture the image, upload it, it's recognized on the back end, and then it's associated, it's essentially indexed to a model. The model is brought in, and the kids get to see what the model looks like as a constructed image in 3D on the surface, which is key. Lego's actually been very forward-looking. They've taken up a lot of this over the past couple of years. Again, Maxim is video on texture rendering, and it's showing the ability to do content version. Basically what they do is we have what's called basically a cloud service, and it's an image recognition service that exists as a web service. So you upload it, and then we return you a recognition result, and then what they do is essentially have an index on the device that downloads new media to the device every time for each new issue, basically. This is the one I was mentioning that's showing how you can integrate an existing product using Vuforia. So what this does is takes a mobile device, you put it onto a little gun, it's a toy, and when it's being used for as a target game. So they're recognizing this, and they can recognize the orientation of the device and understand whether it's accurate for the target. And then here's an interesting one, again, another product uptake. This was actually orchestrated in real scale as a demonstration. So what they do, just as a sort of principle, with augmented reality, when you are augmenting a target, it's most precise when you have the augmentation in the center of the target. For your own work, this will be significant. As you move off, you tend to lose precision. There's a process known as pose estimation, and at heart, it's a statistical process. It's essentially estimating what the pose should be given the known position of this within the camera image. And so typically, as you move off, it becomes less precise. The nice thing about the Toyota app is that they had really refined it in the way that you can take the car well off of this target surface, and it still performs well. And so, as a real-world example, they'd actually gone and built a larger target, gone to the top of the building so that the target was in perspective, and they played out the game so that looking at the height of the building with perspective of the augmentation, that the size of the car was correct, so everything was in scale, basically, which was kind of a neat experiment. And again, Collar is the one, what they're basically doing here is it's recognizing this image. As the kid colors it, you have the ability with the SDK to basically look at the camera frame and to extract the target. It's called a camera patch. You can extract the target area and then analyze the pixels of the target to understand what the color variation is. And so what they're doing here is essentially enabling the kid to color the model. And so as the target changes dynamically as they color in the various areas of the target, it's actually changing the model in real time, which is kind of neat. And then the Ballard catalog, these are very popular. We have a lot of catalog applications. And essentially, one of the innovations that these guys have done, aside from segregating the image, is they'd actually implemented a type of heat mapping. And what this does is they're capable of tracking user interaction and actually the user perspective on the page, so they know where the user is touching, but they also know what they're focusing on. And as I've mentioned, the basic principle of augmenting media is that you are laying something onto the target in the real world. But by doing that, again, you're able to understand what the orientation of the camera is and what the distance, basically the position and orientation of the user relative to the target, and that's how you can get this kind of heat mapping. So you can tell what they're looking at, essentially. So really, the value add for Vuforia is we put a lot of work into optimizing the SDK for mobile devices. We run on everything from Android 2.3 above and the range of iOS devices. And so really the challenge in that, for anybody who's worked across mobile devices, is really developing a consistency of experience, because you have the runtime performance of the devices can differ dramatically, the rendering paths differ. And so a lot of our work goes into optimizing the core algorithms and the rendering capability. As you can assume, augmented reality is a very computationally intensive task. What you're doing is simultaneously you're looking for the image, you're attempting to recognize the target in real time, and then you're attempting to track that, and that's done in real time at 30 frames per second. So the process behind that computationally is very intensive, and it tends to take up a lot of resources. So a lot of our work has gone into optimizing that so that we have a consistency of experience across devices, and that computational workload is not detracting from the rendering and physics and other performance within the augmentation layer. And so within an environment like Unity or working in Android or working in iOS, what it really means is that you're capable of achieving the same quality of rendering that you would expect within a gaming environment or a model visualization environment, and also the physics simulation and the other sort of programming and interactive capability that you would have natively within the app while also performing detection and tracking for AR.
What kind of fidelity do you need in the keying image to be consistent for a read? I mean, does it have to be as detailed as some of the imagery that you have there? Or is it
No. This is, some of this stuff is from early. We've gotten much better at actually being able to pick up a broader variety of images, and I'll give you some examples. But no, I mean, at this point, with the current SDK, you can work with relatively simple images. There's certain types of features that are stronger for tracking than others. Like, for instance, it tends to like corners and edges, sharp transitions and contrast. It doesn't like a circle, for instance. A circle tends to be hard to pick up because you don't understand you can't understand the orientation of the circle because there's no differentiation of the geometry of the feature distribution. So, I think one of the things that people need to understand when you're working in augmented reality is it's still really a crafted type of process or development. And so, a lot of folks look at it and they assume that, oh my God, it's just picking up everything. It's like some kind of magic. But realistically, you do have to know something about the environment you're working in, the type of target that you're capturing, the quality of the target, and also the user's interaction with that. So it's significant to keep that in mind. This is going to show off some of the types of benchmarks that we use. And also, I guess, for the design and development of apps, it's a good thing to keep in mind. So it's a relatively rich target. This is you'll notice we're using particle systems. That's the fire. This is a very high poly model. So this is really what you would expect of like a AAA style, at least within the mobile space, a more rendering intensive game. So you'll notice that even when you have relative movement of the camera, we're capable of still maintaining the tracking accuracy, which is a big deal. Also, it's relatively robust to occlusion, meaning that you can remove areas of the target and it's still, once it's captured it's capable of maintaining that target reference. I mean, basically, as I mentioned, one of the challenges that you get into, and especially working in architecture, is that you're going to have models that extend well above the target, may extend off the target. So some of the benchmarks that I was demonstrating, what you would see with earlier generations of the technology, and this is even away from our stuff, is that as you got further from the target, you started seeing jitter, and this was basically a pose estimation error. We've gotten much better at actually removing that and actually using other areas of the target environment so that you can start bringing things well off laterally and off vertically from the target face.
Is there like a known tolerance?
It's really, again, it's a crafted thing. What you end up doing is there's a statistical estimation that occurs. It's really going to be relative to the quality of the target, the offset from the target surface, and also then you're getting into like lighting and other, ambient characteristics. So there isn't a hard number that I can give you as far as what you can do. You test it. That's really the best.
Have you seen an implementation where the AR sort of hands over to
Dead Reckoning or something?
Yeah.
Yeah, people have done that. There's Augmento's done something with that. And actually, we're introducing technology, I'll show you a demo at the end of this, that kind of solves that problem without using Dead Reckoning. Dead Reckoning would be using inertial and magnetometer, so that once you lose it, you're then looking at really what the internal sensors are telling you about the motion of the device. So broadly, as far as looking at the Vuforia platform, it's an end-to-end platform. It's everything from a plugin that goes on your device to an online target manager that enables you to design and configure and generate the various types of targets that we support. So the target types basically go into planar images, which are things like this, flat images that are rectangular. You can do, obviously, organic images, but really it's going to define it within a rectangle internally within the SDK. User-defined images need to be flat, but they can be generated at runtime. Basically, you're capturing the camera image and you're creating a target from that. That's a user-defined image. Cuboids are basically an arrangement in a manifold shape made up of 6 panels of flat surfaces, and I'll show you an example of this. But for architectural applications and visualizations in internal spaces, they can be very useful because what a cuboid enables you to do, it's basically what we call a multi-target, is to take multiple flat images and then put them at different orientations to each other so that you can capture larger areas. If, for instance, you wanted to put a big model in the corner, you could basically define the one wall as an image target, that wall is an image target, and the floor is an image target, and you array them like this, so that as the person's approaching it, they have a range of perspectives that they can use to capture that. And they can get closer to the target, and they have a better, what would you say, it's a more robust target definition. We can also capture cylinders, which would be a shape like that, or this, which is a sloppy cylinder. And within the cylinders, we can also recognize conical shapes, so where you have a difference within the top and bottom diameters. We have text recognition, and then frame markers are, again, they're a bit like a fiduciary marker or a QR code in the fact that you can derive an ID from it, it can decode the borders. And all of those targets are put into two types of databases. A device database, this one, is actually embedded within the application. You can download new ones and load them, but it's a type of embedded database that basically is activated at runtime. So the advantage of that is that you can have 100 targets at a time, and they tend to be a bit faster as far as recognizing them. And in the cloud databases, it's really, we provide a web services API. You upload them, you can access them via a REST API. Those recognition events are going to occur one at a time, but the advantage is you can support extremely up to 1 million images at a time. So that's something that if you have a really large portfolio of images, let's say they're schematics or they're catalog images or whatever it is, you can provision them within a cloud database and enable you to support and version that online. The range of really rendering and creative effects, we provide you access to the camera image, and you can access it as really a pixel array, a standard set of pixels, and also you can map them to textures. So the advantage of that, as with the Color app, is that you can extract the features of the image that you're capturing and actually analyze those, which is useful. And also you can apply effects. So you could do grayscale. We've had people that have done various types of masking. We've also seen that background texture actually is being used for like head-mounted displays, because you can actually then replicate the background and map it into, so you can have you can do stereoscopic vision, things like that. We obviously have video, and then occlusion management is a neat one. Occlusion management is basically the ability to define areas of the target as buttons, right? We call them virtual buttons. And so if you look at this, where we have the red, blue, yellow, and green buttons, you define rectangles over those, and when they're occluded, when they're blocked by the user, it fires an event. And so the neat thing about that is that you can take a physical surface and basically treat it as an interactive canvas, so that if someone is touching the physical object, you're capable of understanding what area they're touching and what they're blocking. And then the supported development tools, Unity is really our primary development environment, at least among our user community, our developer community. And then also you can use Eclipse for Android apps and Xcode, obviously, for iOS apps. And you can embed Unity into those environments if you want to extend an existing one. Really the advantage of Unity is that you have the rendering engine, the game engine capabilities, the physics, you have everything sort of packaged together for you. And the workflow is much easier. And again, just to recap, platform components range from SDK to the various web resources that we have. We have a set of REST APIs, web services, our development tools across Eclipse, Android, and Xcode. Android Studio, we do support it. And also Unity. And I'll show you some of the web resources as we go forward. So in understanding, I guess, the development of an application within the larger architecture, when you look at these, the dark green are really all the components we're providing. There's sort of Okra, the app assets, the logic, the rendering engine. That's only for native. Unity provides the rendering engine. Native Android and iOS, you need to bring in your own 3D rendering engine. You're providing the content, you're providing the images, we provide the APIs, the target manager is where you can create these targets, and then really all the rest of it, the SDK components and the ability to embed databases, the device database. So let me show you, this is the target manager, or it's a view of the target manager. You create new databases, you can upload images, download your targets, integrate with the app. What the target manager does when you upload an image is it gives you an evaluation of it, so it gives you a rating. We use a 1 to 5 rating just to simplify it. And then it will give you sort of qualifications of the image, right? So this one, on a scale of 1 to 5, is a 2, And the target manager is going to give you some advice as to how to improve that. You can increase the total number of features. You can ensure that all the objects have clear defined edges. Basically, the robustness of tracking and detection is dependent on the density and distribution of features across the target surface. So that's why we tend, when we're demoing, we're using these kinds of things. You see there's a lot of contrast. It's very varied. It's well distributed. Really, the distinction among the ratings, a lower rated target is going to still detect. It's going to, the envelope of tracking performance is going to be less than what you'll get out of a 5. And what that means is the ability for you to move rapidly across the target face with your device camera, or to block large areas of the target, or to rapidly move the target, is less than what it would be with a 5. With a 5, it's extremely sticky and you can do all sorts of stuff. So this is what basically the algorithm is looking at. And if you look at these hatch marks, these are demarking all of what are called feature descriptors. And so you'll notice what they're looking at is all of the transitions, the sharp transitions in the luminance contrast, which is basically this contrast. All the changes in gradient across the image. And so when we take the image and when you upload it, what's happening internally really is it's being transformed to grayscale. The SDK isn't sensitive to color. It's taking everything down into a grayscale. So it's just something to keep in mind. You can often improve images if you have something that's existing and you want to improve the rating by improving the contrast a bit and adding just little, like almost ornamental details. Like if you're looking at this, like up in the Mad Hatter's hat, that little region with the 106 there is extremely feature rich. So it's something that's easy to drop into a target for the purpose of increasing the detectability and the tracking. So the next generation of our stuff, this is what we had demoed recently, is a type of, it's basically the ability to capture real-world context, real-world surfaces at runtime, generate a depth map of those, and then to render onto them procedurally, and also to recognize 3D objects using the same techniques. A lot of this we've developed for the purpose of gaming applications. AR is very popular in gaming, but it has applications also within, I think, architecture and the engineering field you guys work in. And again, it provides a real-time 3D map of a play space, which is a real surface, real space. And what it's doing, just to understand the technology, is principally you're going to use a reference ground plane, as it's called, which is really, you want to start with a flat surface. And what that gives you is really the bounds of the real-world environment that you're going to render onto. The significance of that is that when you're doing this type of technology, when you want to lay an augmentation of a known scale onto a surface, it's good to have that reference plane because what it's going to give you is a consistency in the scale of the rendered object in virtual space, if that makes sense. And also, you want to know the plane that you can't go beyond. You don't want something that if I'm simply like waving it in the air and there's nothing to act as the background, as the, what would you say, sort of it's like the end of the far clipping plane within 3D terminology. It's basically the barrier that you can't go further past. What that gives you then is the ability to use that as sort of a known reference, and when you're rendering onto it, that you can maintain a consistency in scale. Something isn't just going to go infinitely into the background. So, we call this smart terrain. So you're capturing the environment, you're mapping it. That green area is actually dynamically capturing the 3D contours using the features of the environment and the depth map, and then you can render onto that procedurally. You can also render static objects. And you have all the capabilities you would typically in a game engine. You have interactions, you have the physics. Really what it's doing is, again, creating a procedural terrain and adding 3D objects into that, and then you're defining the types of behaviors that occur on there. You're adding the characters. And that demonstrates the ability to recognize a 3D shape and object. So what that does, that technology is a combination of 3D IR-based depth mapping and also then optical techniques that are extracting the features of the environment. So what it's doing is it's capturing a 3D map It uses the Capri sensor, which if you're familiar like with Microsoft Kinect, use Capri. So basically it takes that map, and then it takes the optical mapping that's created, looking at the features that we had shown, the contrast variation, and it maps them together so that you have a coherent image of the environment. And what that tells you is as you move across it, that you can compare the depth map with the optical features, and that tells you what your orientation is to the surface that you've just mapped, and it gives you the pose ability. It gives you that ability to register virtual objects onto that surface. So really, at this point, the suitable context, suitable spaces are indoor well-lit environments. It needs to be able to recognize the features. Again, it needs a reference plane, which is tables, floors, other large flat surfaces. They don't need to be the extent of the environment, but they want to start with that as your reference. And then objects with detail and texture. So it's not going to work well with like the white surface of the tables here, but it will once you start adding things that have a little more detail to them. Right. Some of the constraints. This is basically what you want to keep in mind with any of this, and it applies to any form of augmented reality, is that the features of the target that you're using really are what enable it to be recognized and tracked, so that when you remove those, you reduce your ability to track effectively. So direct sunlight knocks out features because it's introducing glare. Shadows knock out features because they're too dark and you can't see the features. IR absorbent reflective materials, this is specific to Capri, are going to basically introduce noise to the IR signal. Very small objects are going to fall below the resolution of the mapping, and transparent objects are not reflecting features. So,
how small is very small?
Very small is going to be
Like a golf ball?
no, you can do golf balls. It's like think dimes, something like that.
Okay.
And truthfully, if you're close enough, you're going to get it. What we look at, and these are really design recommendations. You can work with, if you have a specific case that it's going to be, the apparent features are going to be consistent. You can do that. What we recommend against is using something very small and then expecting the user is going to be able to walk 10 feet away and still see it. This technology actually is capable of calibrating for close versus further types of applications. This one is really used at like my distance to that tabletop, but you can calibrate so that you can capture further terrains. And then here's this again. It's using the device camera. It's using a depth synchronized view of the scene, and we're coming out with a developer kit. That you can, if you go to our developer portal, which is developer.vuforia.com, there's a contact form, and just make an inquiry. We're going to make them available in the spring. And again, the Capri developer kits are coming from PrimeSense, which is one developed for Microsoft Kinect. Do you guys have any questions? We're running low on time.
Yeah, you said that shadows would obscure the readability. Is there a way to use a shadow to actually enhance it? Like, because if you have shadow as contrast, which is sort of the requisite for the first version, if you were able to control the light.
Yeah, theoretically, that's an interesting, right. If you had, let's say you had a 3D surface with nooks and crannies.
Yes.
And so you change the lighting, and what it's going to do is actually enhance the contrast variation. You're right. That's a good, interesting. Yeah.
Okay.
Any other questions? Okay, thank you.
Thank you.